In this short tutorial, I'll show you two examples where we apply the first law of thermodynamics. Before we do the examples that have been prepared, remember that the first law of thermodynamics associates the internal energy with the process that may lead to its change. More formally, the law states that the change in internal energy of a system equals the net heat transfer into the system, written as Q in the equation, minus the net work done by the system. And that's neatly summarized right here. In question number 1, you eat 100 food calories worth of nuts. How high would you, at 65 kilograms, have to climb to work these 100 calories? Now, we won't be using the first law formula in this particular example. We will in question 2. But I do want to review how to calculate work. Work is a major component of the first law, so it makes sense to start here. Work is equal to the force times the displacement. And over here we're being told that 100 food calories worth of nuts have entered your thermodynamic system. 100 food calories is the same thing as 100 kilocalories, represented as kcal. We need to find out how much work is required to get the equivalent of this amount of energy. Now, when you calculate work normally, you find out what it is in joules, although there are other units that you can use for energy, and that being calories being another one. But normally we use joules. So what I will do is convert 100 kilocalories into joules. 100 kilocalories, the conversion ratio of calories to joules is every 4.2 joules makes 1 calorie. But first we have to make this into calories before we can use that conversion ratio. So we have 1,000 calories makes 1 kilocal. That cancels out. And as I said earlier, 1 calorie is equivalent to 4.2 joules. So by multiplying all this out, we should end up with a value that's in joules, and that's the total amount of work that we need to perform to burn off or work off this consumption. We end up with 420,000, or 4.2 times 10 to the power of 1, 2, 3, 4, 5 joules. Now remember, I said work is equal to the force times the distance. And force is equal to mass times the acceleration. Since we are climbing, the acceleration is the acceleration due to gravity being 9.8 meters per second squared, and the mass is your mass, 65 kilograms. Multiplying this out, we should end up with force. And then we multiply it to the distance, which we don't know. That's what we're looking for. How much do you have to climb? So we'll take that value right there, the one that we just calculated, and make it equal to the work that we calculated as well, the one that we converted. So 65 kilograms times 9.8 meters per second squared, that gives us newtons, those units, multiplied to the distance d, which represents the climb. So the value on our screen divided by 65 times 9.8, that's to solve for d, and we get a distance of around 660 meters. 660 meters needs to be climbed in order for you to burn off 100 kilocalories. Now let's actually apply the formula with this next example. In a certain process, 1.5 times 10 to the power of 5 joules of heat is added to an ideal gas to keep the pressure at 2.0 times 10 to the power of 5 pascals, while the volume expands from 6.3 to 7.1 meters cubed. What is the change in internal energy for the gas? So we are looking for that value, and we are told the heat that's added to the system. It's 1.5 times 10 to the power of 5 joules. The work needs to be calculated. Remember, work can be calculated in many different ways. The way I showed you in example 1 is the most basic way that we've learned. But work, as we learned in our previous tutorial, work can also be calculated using this. where delta W is equal to the pressure times delta V. So let's write that down. The change in W is equal to the pressure times the change in volume. So the pressure has remained the same, and you only use this formula when the pressure is the same. When the pressure has changed, you use a different formula, as we learned in that previous video. So the pressure remains the same. Remember that 1 Pascal is the same thing as 1 Newton per meters squared. And then we multiply this to the change in volume being 7.1 minus 6.3. That's a difference of 0.8 meters cubed. Now the reason why I told you that it's newtons per meters squared is so that you can see the units corresponding here. These meters units cancels out with 2 of these, and we are left with newtons times meters, which is equivalent to 1 joule. Multiplying these out should give us a value that's in joules. 2.0 times 10 to the power of 5 times 0.8, and this gives us the amount of work being 1.6 times 10 to the power of 5 joules. So we will subtract this value with that value to get the internal energy. 150,000 minus 160,000, and that's equal to 10,000. Delta U is equal to negative 10,000 joules. And if you want this to the correct number of significant figures, you should put it in scientific notation as negative 1.0 times 10 to the power of 10. To interpret this negative, that means that the internal energy of the gas has been decreased by 10,000 joules. And there you have it. Now you know how to apply the first law of thermodynamics. If you'd like to see another example, let me know in the comments section below. I have one more example prepared,
and we'll gladly upload it on your request. Thanks for watching.